Did you ever wonder what a unit step response of a second order system looks like? Imagine hitting a system with an input that jumps from 0 to 1. Are you curious about what happens next? I was in the same boat not too long ago. In this video, we'll break down how to derive the closed form solution for this in the time domain. Stick around because I'll guide you step by step through the whole process. And if you like what I'm doing, please like or subscribe. Now let's get serious. Welcome back. Today we're talking about the second order system and its unit step response. So a second order system, as we know from last time, can be written down as such. It's xs over rs equal to b omega n squared over s squared plus 2 zeta omega n s plus omega n squared. Now you might wonder, how does a solution in time domain look like of this system? Well, for this we have to dive into the S-plane representation. The S-plane representation, I will draw it in the middle, looks like this. We have the real axis and the imaginary axis. Now you know that the roots of this denominator have to be on the left half plane, meaning the real term of the roots have to be negative. We can draw an arrow which we name omega n, and we can draw an angle which we name alpha. Now I can project this omega n onto the real axis and name this term omega n multiplied by cosine alpha. In fact, this omega n cosine alpha is omega n zeta. Some people refer to this term as well as sigma. Now, the same can be done for the imaginary axis. The imaginary axis is the damped natural frequency, which is equal to be omega n by the square root of 1 minus zeta squared. Now we're looking at the steady state error of the feedback loop. Now what do I mean by feedback loop? By feedback loop I mean we have an input Rs with an arrow term E of s and a feedback Cs, and we're looking at the plant GS, which goes out here. This is a node, and we have a unity feedback. So H of s is basically just 1. And I would like to look at the steady state error of this feedback loop. The imaginary axis is nothing else than basically j omega n. Now the real axis is as well called sigma, and this comes from this term because the roots are minus sigma plus minus j omega n, and then 1 minus the square root of 1 minus zeta squared. If the roots of this function lie on the imaginary axis, we call the system marginal stable. Marginal stable means that if I hit the system with a pulse, just very briefly, you can imagine basically the system being at rest, you hit it with a pulse, not a step response, just a short pulse which excites the system. How would the system react to this short pulse? Now, the system, if it's marginally stable, will react in such a way. It's marginally stable. So it's basically bounded. If you do the same thing for a system where the root lies much higher in the natural frequency, of course, the oscillation will be much higher too. This is just a schematic drawing. I'm just trying to illustrate to you what marginally stable means. And the root lies here, and we hit it with a pulse. The system reacts like such. You have a decay that oscillates pretty quickly. On the other end, if the root lies more on this side, meaning the root has a more negative real part, the system decays much faster, same frequency, but it dies out very fast. If I have, for instance, the root being here, you can see that the system decays in the same rate, but the frequency with which it decays is much slower. So because natural frequency is lower. If the system lies here, as you can expect, the decay is really fast, but the frequency is really slow as well. If the root lies on the real axis, that means the system is critically damped, and the damping ratio, zeta, is exactly 1. In this case, you will see if it's exactly 1, the imaginary term will simply go to 0, because the natural frequency itself is not 0, but the minus omega n is exactly reflected on the real axis. In this case, the decay would look like such. If the root lies much more on the left-hand side, then the decay is happening again much faster. In the unstable region, if a root lies here, for instance, you would have, instead of a decay, a growing. And this growing, the frequency stays the same here, but I'm just illustrating you, the frequency is high and it's going off. And if it's going to be here, the frequency is much slower than in the first one, but going off as well. Now, on the other end, you can ask the question, what happens if the root lies on the real axis, but on the positive side? The steady state response of such a system, it looks like this. So it's basically going off towards infinity right away. And this wraps basically up the representation of a second order system in the S-plane. So again, we would like to apply a step input on this system. How do we do this? We have xs on the left-hand side multiplied by omega n squared s squared plus 2 zeta omega n s plus omega n squared multiplied by 1 by s, because r of s is equal to be 1 by s. And what we have to do now is we have to set this one equal, because we see there are two roots here, which might be complex conjugated roots, and one root from the step. So we split our system up in k1 over s. So again, applying partial fraction, k2s plus k3 over s squared plus 2 zeta omega n s plus omega n squared. Okay, so what we do now, we need to figure out k1. From a quick glimpse, I can see if I multiply the system by s and plug in s equal to be 0, because it's one root of the system here on the left, I can claim that k1 will be remaining here. I plug it in, this whole term vanishes, and in this term I just have to plug in to solve for k1. So we can see that k1 is equal to be, let's see, 0 plugged in here, 0 plugged in here, omega n squared over omega n squared. That makes k1 equal to be 1. Now, we found one variable. I'm making this a 1. Okay, in fact, let us multiply quickly by this term on the left-hand side. So we have s squared, just making equal, s squared plus 2 zeta omega n s plus omega n squared over s, and multiply this term plus k2s squared plus k3s over this whole term. It doesn't really matter because it's a common denominator now. We have s squared plus 2 zeta omega n s plus omega n squared. You can see now, if you want to get from this term the same which is written on the left-hand side, only in omega n squared, this one has to be minus 2 zeta omega n, and this one has to be a minus 1. Do you see where I'm coming from? You don't have to always plug in the root and solve for the complex, equate for the real and imaginary part. Sometimes with a quick glimpse and by using this shortcut, you can solve for k2 and k3 in a very easy way. Now let us plug in those numbers which we have here. We would like to split this term up into two different pieces. Let's try that. So that's going to be equal to 1 over s minus s plus 2 zeta omega n. Now I have to rewrite this denominator in a bit of different way, and I can do so by applying s zeta omega n, square these two things, and apply omega d squared. if you apply omega d squared like here, you will see you will end up, if you plug this in here, with the same equation as down here. Now you can see that I wrote down the Laplace transformations of two important functions, which you can see here as such. And what we want to do is we want to split this one up in two parts. One stays with the s plus, it's going to be 2 zeta omega n, and the other one we write separately as zeta omega n over s plus zeta omega n squared plus omega d squared. All right, now what I want to do next is I need another omega d in here. So I'm extending this term by omega d. I can do that. Okay, and now the xt, finally, the unit step response of a second order system can be written out by applying the inverse Laplace on 1 over s, which is simply 1. And I can look in this term. This is looking more like the cosine rule because I have two things in the numerator, and it's going to be minus e zeta omega n multiplied by the time, because the a in our case should be negative, but it's positive. Whatever comes in front here doesn't really matter. That's a minus sign over here. And we have a cosine term. Let's check this out. The cosine term should be an omega d t. Omega d t. Why? Because the b is squared down here. And on the other end, we have this term here, which is the sine term. It's going to be e exponential minus zeta omega n t. That's this part inside here. And I can see as well that the b and the b over here match. So these two terms, I can flip this basically. Now these two match, and therefore there's something coming in the front, so I'm leaving a bit of space. Sine omega d t. And in front, it's very interesting now to see, is basically this guy over here, which is a bit hard to solve for on the first try, but it is basically zeta over omega n d. I make a little side calculation down here. It's zeta omega n over omega d, which is omega n, 1 minus zeta squared. Omega and omega n cancels out. So it's simply zeta over square root of 1 minus zeta squared. And voila, you're done with the second order system unit step response in time domain as a closed form solution. Isn't that wonderful? All right, that was it for today. I hope you enjoyed what I was teaching you today, and if you like what I do, please subscribe to my channel or hit the like button. See you next time.